Welcome to Composites Modeling using numerical methods, Module 6. Today we'll be covering 2D plate elements, the processing, and the ABD matrix. Welcome, Mr. Wei, again, for helping me through this tutorial. So what is that we're trying to do? We're trying to represent a 3D structural plate, and we want to represent that as a 2D plate. And what we're trying to do there is we're trying to track the reference midplane, and we're going to assume that the behavior and deformation above the mid-surface and below the mid-surface will follow closely that of the mid-surface. Not exactly, because the deflections will vary linearly through the thickness. And also, we have several assumptions that this 2D plate theory is based upon. Number one, the normal to this plate will remain perpendicular to the mid-surface through the deformation process. That is true for thin plates. The second assumption is that the plate thickness does not vary significantly through the deformation process. In other words, the transverse shear strains and the through the thickness strain, those strains are nearly zero. And this is considered a plane stress assumption. For a thin plate, the transverse shear stresses will be close to zero, and the through the thickness stress will be close to zero. And that's because we have a very, very small thickness of that plate compared to the other two dimensions. So the learning objectives of this particular tutorial and module is to gain a top-level understanding of how internal forces, bending moment, and shear forces relate to the strains and curvatures of the system. From there, what we want to learn is how to input a matrix. This ABD matrix is a constitutive equation that relates the internal forces for a plate to those of the strains of this plate. And we can learn how to directly input that into the software. And also we can perform the calculations using an Excel sheet to show that we get equivalent answers. We want to use these examples so we can learn about how this will be done in the software, but also using Excel. If you recall, we discussed earlier in a previous module, 4 and 5, the free body diagrams of a plate. We discussed that there are 8 resultant forces for a plate. NXX is a membrane force per unit width in the X direction. NYY is the membrane force per unit width in the Y direction. And NXY is a shear membrane force per unit width in the in-plane XY plane. And then we have 2 transverse shear forces. They're also per unit width. And then 3 bending forces. 2 are bending moment forces, and the other one is a twisting moment. And here is the relationship between the resultants and the stress field. If you recall, in beam theory, the forces will be integrated through the cross-section. But in plates, the resultants that you get, those internal resultants that react external forces applied to the structure, are going to be integrated just through the thickness. So the in-plane plate forces, if you recall, were NXX, NYY, and NXY, and those quantities are per unit width. Very similarly, we discussed in the previous module that the transverse shear force applied is also per unit width, and the bending moments that we're considering are also per unit width, as well as a twist per unit width. And so we want to take these 8 resultants and be able to relate it to the curvatures and strains in the plate. So when we look at the strains in the plate, based on another composites tutorial, lecture number 4 in the playlist for composites, you can see here that the strains in the plate are going to be equal to the mid-surface strains. So the strains are occurring at the mid-surface of that plate, plus the curvatures of the plate times Z. So notice here how the strains in the plate, anywhere in the plate, are a linear function of the curvatures against the curvatures. And so the mid-surface strains are added to the curvatures times Z. And this is a fundamental assumption of this theory. And this is not very different from beam theory. It's just that you're probably not used to seeing Y because we're considering a beam in those cases. So this will have been 0, and you will have just seen the first row. But here, we're considering the total behavior of the plate in 2 dimensions, and that completely relates it to the mid-surface strains and the curvatures. But now that I have these quantities defined, I need to find a way of relating the resultants of the plate to these strains. And that's where the ABD matrix comes from. And this is extensively discussed in a different link to the video that I'll provide in the description. So the full understanding of the ABD matrix is provided there, but I'm providing just an overview here because these modules go along with the Composites lectures playlist. So the ABD matrix here, what it does in essence is for any stacking sequence that's provided to you with material properties defined, the A matrix, the B matrix, and the D matrix can be fully calculated. And this ABD matrix fully depends on the stacking sequence, the thickness of each of the plies, and also depends on the material system. The material system and the ply angle fully defined in Q bar, and then the location of the ply will define A. And so A here is considered the extensional stiffness, and the extensional stiffness relates the resultant forces to the in-plane strains at the mid-surface, but also the in-plane resultant forces are related to the curvatures. That is not something that happens in isotropic materials, but in materials where you may have asymmetry about the mid-surface, then in those cases, a B matrix will appear. This B matrix relates the bending behavior, the curvatures, to the extensional forces. In other words, if I were to apply extensional loads to a plate, it will also bend. Pretty much that's what will happen. For a symmetric layup, the B matrix will be 0. And as you increase the number of plies to very large numbers, the B matrix will approach 0. That's another consideration that you will see often. Another point I want to make is that the moment resultants are related to the mid-surface strains as well with the same B matrix. Meaning if I were to bend a plate, the mid-surface will also experience some stretching. And that's counterintuitive, but that is the case for asymmetric plates. And then the bending moment resultants, those are related to the bending stiffness times the curvatures. And in beam theory, isotropic materials, you may have seen that. You may have seen that mxx equals EI, the modulus and the moment of inertia, times kappa x, the curvature. But for a plate, again, number one, ABD is fully known because we know the stacking sequence, we know the ply angles, we know the thickness. So we should be able to then fully populate this and fully understand how the plate bending resultants and in-plane resultants completely relate to the strains and curvatures. Here's a summary of the ABD matrix. And again, that can be calculated using this formula, and I'll provide the Excel sheet in the description. But you want to follow the other video that goes into very deep understanding of the theory so you can better understand how this is used. So the case study you want to study is this stacking sequence with these unidirectional properties And what we want to do is look at how that will be applied to a simple problem. So let's look at the problem I want to study. I want to study a plate that's 20 inches long. The width is 2 inches. An 80-pound force is applied transversely and 90 pounds extensionally. So really what you have there is that the 90 pounds is in the y direction. So 90 divided by 2 gives me an XX, and that's an error. 80 pounds transverse, that's going to be 80 divided by 2. And that's QY because he's acting the Y phase in the Z direction. And that'll give me the distributed load per unit length. And then I have a bending moment. And the bending moment here is 80 times this distance here, which is 10. So 80 times 10. But I have to divide it by the width to get it per unit length. So I have 80 times 10 divided by 2. And so if I were to now run that, so let's do that really quickly in Excel. Here, that what you will do in this Excel sheet is that you specify the material properties here, E11, E22, Nu12, G12. Those were provided. You can modify and add as many as you want. Under laminate, I have fully defined the stacking sequence from bottom to top using the stacking sequence I provided in the PowerPoint file. Just by doing that alone and I specify the material ID, this particular software, with the loading applied, so I put the correct numbers in here to be consistent to what we just discussed. So NYY was 800 divided by 2, that's 400. 90 divided by 2 is 45. And when I run that analysis, I'm able to find the strains in each of the layers. So the 0-degree layer, you can see the angle 0, 45 minus 45. It produces the strains locally along the fiber direction for each of the layers, and they're all provided here. It also provides the ABD matrix, correct? So it provides the ABD matrix, also the equivalent laminate properties, how the stack will behave if you were to do some tension test. Obviously, these are estimates, so it's not going to be 100% accurate against testing, but it is an estimate. And so you can see here how the strains vary from layer to layer when the bending and extension loads are applied. So as you've seen, we simulated this model really quickly in Excel. You cannot do this for a more complex problem, but this for the purpose of illustration. And so now what we're going to do is we're going to move into the ABAQUS portion, the software portion. By the way, all other softwares can do the same thing. We're using ABAQUS as an exemplar of how this could be done. So we're going to use ABAQUS. We're going to simulate the behavior of the stack by providing ABAQUS the ABD matrix, and then we'll compare the deflections against number one. We'll also do the same thing by modeling the stack in ABAQUS ply by ply. So we're going to do two methods. The one is specifying every single ply in the stack. The second method, the ABD matrix, will be provided, and then we'll compare all the results. So I'm going to pass it to Mr. Wei, who's going to help us through all that. Thank you for your attention. I hope you're learning a lot through these modules. And we're looking to look at a problem of optimization next in the next module.
Today I'm going to show you how to use ABAQUS to simulate the composite material and compare with the ABD matrix that I calculate in the Excel. And then later we will input the ABD matrix into the ABAQUS and then compare the deflection with the composite when we apply the composite material. In this case, we are going to simulate a KW beam that one side is clamped, the other side is suffered unilateral tension, and then the load in Z direction. Then we focus on the cross section at the center of this beam and check the string layer by layer and also compare the deflection. The ABD matrix has listed in the this slice, and also there will be the Excel provided to calculate the stiff matrix here. Okay, then let's first to simulate a model that for the composite material, how we usually make, just assign the composite material. So the part we choose the 3D shell panel. The size is 2 by 20. And then I want to make a partition because later we are focused on the center. So if we make a partition, it's better for later and analysis. So this line represents the center line. Then we assign the property. Here, use the laminar, and then we can go to the Excel to just copy the material. The other material property list here. Of course, you can use the engineer constant one, like this one. Mm, But lambda is good enough. Okay, now we assign the material already. Total have 22 layers because the composite is symmetric, so we only need to assign 11. We use conventional shell. The region is this region. Right click so you can assign all the properties together. And the thickness is uniform 0.09. The rotation information is in the first sheet in Excel. So we select the first 11 layers. Copy paste. Okay. This is okay. Then assemble. Yep. This is static one. Okay. Then we are going to create another view output. Because we are going to see the composite layer by layer. So we want to make the domain the composite layer and select the stress and the strain. We will check later. And also we want uh, the section force and the section moment. Just click the SF on. So we can double check if we assign the right boundary condition. The interaction parts. For this part, I want to set 2 reference points, although it's not really necessary. Then create a set. Reference 1, reference 2, reference 1, reference 2. Okay, then I'm going to make the constraint to let the surface 1 and the reference 1 move together in X direction. Also for the other directions. Okay. Load the boundary condition. So we are going to climb one side. We're going to climb this side. And then also we don't want like this the left boundary move in X direction. So we just fix in X direction. Then here we're going to apply the load. So we have the uniaxial load, use the shear load in Y direction, 45. Yes, 45. Okay. Then create another shear load that is in the direction. Um, so we choose the transverse negative 40. Okay. So then we're going to mesh it. We can use the quadratic structure one. The element size we make it a 0.1. We can mesh it and check if we use the right elements type. Reduce, we don't need to reduce this stuff. Okay, the property since I think I missed one thing that needs to make a symmetric. Okay, don't forget to click this on. Load induction, mesh job. Okay, I think I have done all things. I just should submit this one. Okay, we can double check the results. First check the section force in two direction. So you can click this one, then probe the value, node. So you can say it's about 45, it's 45, so it's good. Then we check the momentum. Um, then we're going to check the center line. So as we have make a set, oh, we haven't make set, sorry. I forget one thing. We're going to make a set called half, so that later we can just leave this section and then to see the cross section either. And then we just quickly rerun it. Okay, we see the result. We have the heart. You can see this one. We check the moment. Should be about 400. You can see this. Okay, that's good. Okay, then we can start to look at the string. So click the results here. Select section points. Here output is a string. String choose, we'll first see the even one. Then the bottom part, we can just check the value. That is about the 0.04. Then to see the Excel. Okay, so for the Excel, this first sheet shows the composite angle and thickness. Second one is the material property. Third one is the loading information. And then we have the uniaxial load and also have the load, have the momentum at the center line. And then the fourth sheet is the calculation. So we scroll down to see the highlighted parts. Here is the layer by layer string. Then for the E11, it's about negative 4.6. So we see this one. It's about negative 4.6. Okay, it's good. Then layer 2, 3. Let's just randomly choose 3. The third one, layer third, 0.038, 38, 0.0038. A little bit deviated. Let's choose another one, like 0.4, layer 4, about 0.03, 0.03. Okay, that's correct. Um, yeah, we can. So that's pretty much about our Excel. We can also check the E22, then go to the composite like layer 1. E22 is 139 something. Okay, that is 139. That would be okay. So first we have finished the first task. That's compare the layer by layer results with Excel. They are pretty match conversion. Then second thing is we are going to assign the ABD matrix in our ABAQUS and then compare deflection with the first case. So for the ABD matrix, actually it's a stiffness matrix. So we can just go to the next sheet. So here list the matrix information. Alternatively, you can go to the website called abdcomposite.com. Then you input the material property here, like E1, E2, G12, and also the how many layer you want to apply, then the symmetrical information. And in the end, it can give you the matrix. Then you can copy it like Excel, then you can put it. Then you can double check whether this data is similar or similar to this one. I think this should be very similar. Okay. Then we go to our ABAQUS. The only thing we need to change is the material property. So previously we assigned the composite layout. So here we just close it. Okay. Then to assign the ABD, we are going to click the section and then go to shell. General shell stiffness. Okay, here is what we need to input. Then we just copy the thing here. Okay. We don't need to change other thing. Then we are going to assign the material property to it. So click section 1. That's done. Then we just run the job. We call it case for ABD V2. Okay. Yeah, see the results. As for this one, we cannot output the stress strain information, so we just compare the diffraction. The quick way is you click the viewport, click create, and then make it horizontal. Maybe not better, maybe better vertical one. Okay, so this one you can choose the composite one. This one you can choose the ABD one. Then you compare the diffraction for the U1. And then we can save the view in user one. Save current view. Then click one fraction. Also, this one we choose U1. Okay, you can see this two control and results and it's pretty much U2, U2, 1 point, yeah, almost the same. U3, U3, 3.7 something, 3.7 something. Okay, that's pretty good. So you can see the diffraction is very good. You can also click the same points and then plot it to see whether the two curves converge or not. Okay, we finished the task 2. Thank you for watching.